So I think the recording has started by now.
Yes.
So welcome to the week 5 of the problem solving sessions in this course of parameterized algorithms. And today we are going to look at the assignment questions of previous year's uh, week 5. So let's go to the assignment questions and we will look at the topic of tree width today, majorly the topic of tree width. So I'm showing you the questions. So I'll make it bigger. So this is the first question. There are a couple of questions, and I think today we are going to finish earlier than the 2 hour limit. So I'll let you read the question.
So can you give a small overview of that? How are they decomposing the graph into this tree?
Okay, fine. So let's first look at the tree decomposition. I'll tell you the properties of tree decomposition. So let's first uh, 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 copy this figure. Somehow today your audio is slightly muffled, but I can hear you. That is fine, but it is not as clear as other days.
Okay. So I'll try to log in from a different system then.
Okay. So here is question 1. Uh, First, I'll write the definition of tree decomposition. So you have a graph and you generate this tree from this graph. So this is a valid tree decomposition of this graph. And tree decomposition is valid if, I'll write it down, the tree decomposition has the following properties. So the first property is that every vertex is in some bag. So these nodes of the tree decomposition are called bags. So let me just write that as well. Nodes of the tree decomposition are called bags. So the first property is that every vertex should have some bag. So every vertex is in some bag. Second property is that every edge is in some bag. So both the endpoints of every edge should be in some bag. And then you look at connectedness of the bag. So this, I'll call it connectedness of bags. It means that those bags which contain a given vertex should be connected. So connectedness. So if a vertex appears in multiple bags, the bags containing that vertex form a connected subtree. So what else? And okay, so what is the tree width? So after you have formed this tree decomposition from a graph, so we associate a parameter called tree width with this tree decomposition, and the width of the decomposition is the size of the largest bag minus 1. So in this case, what will be the tree width?
Yes, so I cannot hear this properly. That what is the tree width? Uh,
So the tree width of a given tree decomposition is the size of the largest bag minus 1.
oh, I see. So the largest bag here is 4. So 4 minus 1 is 3.
Yes.
So
Is my voice clear enough?
yes, now it's clear. Now it's clear. So I have a doubt here that is this decomposition unique or we can have different decompositions?
It could be many possible decompositions are possible for a given graph. It need not be unique. As long as the properties are satisfied, we'll call it a valid tree decomposition. Minus 1. All right. So we have understood what is a tree decomposition. Uh, Fine. So let's go back to the question. So the question says that you have been given a graph and a tree decomposition, and you have to convert this tree decomposition into a simple tree decomposition. So what is a simple tree decomposition? Uh, so let's see what is a simple tree decomposition. So in a simple decomposition, no bag is a subset of another bag. Uh, uh, so to put it in perspective, that if there is a smaller bag which is contained in a larger bag, then that is not simple. So simplicity requires that no bag is a subset of another bag in the decomposition. So now we can see that in this decomposition, there are bags which are subsets of other bags. For example, this bag AD is contained within this bag. So ABD is consisting of three vertices A, B, and D, whereas AD has two vertices A and D, but this is a subset of ABD. So this is not a simple tree decomposition, and it is possible to convert it into a simple tree decomposition while also ensuring that these properties are uh, not violated. These properties are maintained. So there is a way to convert a given tree decomposition into a simple tree decomposition. Okay. So so we have to convert it into a simple tree decomposition, and there are a couple of options. Uh, so first, identify that which all bags violate simplicity.
Uh, so um, so we should focus on the larger bags because there are more chances of getting the things violated. So like say the in T1, T2 is included and T3 is also included. And then we can, so probably we can do this thing recursively also, like say, and in T2, so then AD is included, and then in AD, nothing is included. So therefore, yeah, so the violated are the T2 is violating the property, T3 is violating the property, T4, and then T5.
Yes. So the day, yeah. So let's look at the options once again. First, uh, maybe so looking. So what I will do, I'll copy these options and put it. Uh, uh, Maybe here only we can see. So another option. Okay, let's see the first three options only. Okay. So important thing is not, so first thing is it, in the option we have to check that whether there are two bags which are one is subset of the other. But in addition to that, we have to also ensure that the tree decomposition is valid. So one can do that with some trial and error. For example, let's say I'm looking at option one. I don't see any bag which is a subset of another bag, but but it is not even a tree decomposition, because uh, we want for every edge in the original graph to have a bag that contains both its endpoints, and there are only so few bags here. So let's see. Uh, so for AB there is a bag, for AD there is a bag, for AC there is a bag. As long as bags are concerned, DF, okay. Uh, AG is also there, AC is also there, okay. What is the answer? The answer is this one, GPQ. Okay, so this is fine. Sorry, I take it back. So this is a valid 3D composition. Uh, what is the answer? D, TF, ACG, and GPQ. ACG and just okay. So, yes, okay. Connectedness, CCDD. So it is quite cumbersome to sort of do trial and error and see that which of these options is correct in terms of uh, maintaining all the decomposition properties as well as the property of simplicity. So we'll not go into doing that trial and error because that will take a lot of time. So what we will do is we will see how one can systematically convert a tree decomposition into a simple tree decomposition. Okay, so let's go back.
Yes.
So first thing is we'll try to see that which are the low level violations. So let me copy this figure once again. Uh, I think it is already copied. So what I mean by low level violations is that, so what is the smallest bag where a violation is detectable? So for example, this bag T4, it has a violation because T2 is containing. So T2 is a superset of T4. So that's at T4 there exists a violation of simplicity. Okay. All right. So we have identified, but is there any other small bag, a bag of size 2, where there is a violation? How about T5? T5 is also a bag of size 2, and T3 T3 is a superset of T5. So by similar
Yes.
arguments, that is also a violation. But first, fix one violation at a time. So what is the meaning of fixing? The meaning of fixing is that you drop the smaller bag and you drop the smaller bag and make the two children of the smaller bag as children to the larger bag. Okay, so what this will become is like this, that so sort of these two gets merged in some sense, and you drop the smaller bag. And in the process, is it possible if we do this? So first, let us do this, and then we will verify that in this process we will not violate any of the tree decomposition properties. So we get down from this original decomposition to this decomposition. So A comma D, that node is dropped because there is a violation at that node. It need not have any direction. It's simply a tree. Okay, so this is T2. T4 is no more there. There is T6. There is T7. And rest of the things are as it is. Of course, we have seen that there are violations and we will take care of these violations as well. So we have come here. But first thing is to convince ourselves that in this process, we have not violated any of the tree decomposition properties. Uh, so first property is that every vertex is in some bag. So this is a tree decomposition. We came down to this. So the property that every vertex belongs to some bag, does it still hold?
So, like here, which vertex is remaining and which is not included in any of the bag? Because if we follow the process, then we have not done anything, any major change here, except removing the vertex T4.
Yes. So if there was a vertex which is no more in any of the bags, then that vertex wouldn't have been a part of any bag in the original decomposition also, because we have not deleted a bag which contains a vertex uniquely. So we have deleted a bag which contains vertices which are contained in other bags also, which we have retained. So all the vertices, the property that every vertex is in some bag is true. Similarly, all the edges belongs to some bag is also true, because we have only deleted a subset bag, whereas the superset bag is retained. And the other property, that connectedness property, that connectedness of bags, is it still retained? So,
So connectedness of the bags.
so the vertices that we have that have been part of the deleted bag, if at all they became disconnected, so there is no way they can become disconnected, because the parent, the children of the deleted bag are made to connect to a super bag, superset. So if it was the case that there, for example, D is here, D is also here, and D is also here. So since we deleted this, that means that D must have been here also. And because we have connected uh, a bag containing D, so all the bags containing D are now getting connected directly to the larger bag containing D. So connectedness cannot get disturbed.
Yes.
All right. So this is the first step. And we have verified for the first step that with this operation, we cannot disturb the properties of the decomposition. Now we come to this guy again. So this is a subset of this bag. So you can delete it. So once we delete it, then we'll be left with, we have to connect its children. There is only one child in this case, to the superset bag. So we make this connection. Now, is there any bag? Yes. So you had identified earlier that EBD is a bag which is a subset of ABCD. So we can delete this as well. So if we delete this, we have to make its children child of the super setback. So we'll do that. T2 is no more there, and these guys can directly connect to the parent. Okay. Is there anything else we can do?
So, like in this case, at least this subset property is over. I mean, no bag is a subset of another bag. And moreover, I think that all the edges have also been covered.
Yes. Did you ask a question? Because I didn't hear you the last sentence.
No, I said that all the edges have been covered, and no bag is a subset of any other bag. So,
Yes, yes. So at this point, we do not have any violation to the simple tree decomposition property, and we can output this. So let's look at the options. So the first level we have ABCD. Second level we have uh, ACG, DE, and DF. And the third level we have GPQ. Yeah. So the first, yeah, this is the answer. This is accepted answer. This is exactly what we have got. So this is the first option A, I think. But anyhow, so this is the way to sort of convert tree decomposition into a simple tree decomposition. It's very straightforward. Okay. So let's move to the next question. So this is a problem. It's called the max leaf spanning tree problem. So you are given this graph. So this is a graph G, and there is a K. There is an integer K, which is 5 in this case. So the question is it possible to find a spanning tree in this graph having at least 5 leaves? So I'll write down what is the definition of max leaf spanning tree. Let me copy this figure. Uh, then we look at the question. So here is the definition. A graph is given to you. Additionally, a number is given to you, which is K. And the question is, uh, does there exist a spanning tree of G with at least K leaves? So this problem is called the max leaf spanning tree problem. So you know that the spanning tree can be found in polynomial time.
yes, yes. Uh,
But here he was additionally giving condition that there should be many leaves.
yes. So, minimum spanning tree would be the acyclic subset of the edges and connecting all the vertices.
Yes.
So, all the vertices should be connected and should not form a cycle. And so therefore we can start with a single bag comprises of all the vertices, and then we can start splitting it in such a way so that we should it should form a spanning tree, and with the k number of leaves, there is 5 number of the leaves, so that is the requirement. Mhm.
Yes.
Connecting all the vertices. Yeah.
Yes. Yes. So we somehow want to use this tree decomposition thing. So we somehow want to get a tree decomposition of the graph so that from the tree decomposition, you can derive this maximum leaf spanning tree. Okay, so let's go back to the question. So as far as the definition of max leaf spanning tree. This is the definition. Let's look at the question. So in the process of constructing this tree decomposition, they use what is called BFS. So they compute the BFS tree of the graph. So the BFS tree of the graph looks like this. Let me copy this as well. And then from this BFS tree, they will construct the tree decomposition of the graph, which has bounded width. That is in this case 2k minus 1. But let's look at how does the BFS tree help us uh, in constructing the tree decomposition first. Okay, so let's okay, fine. So first step is from the graph, you just run the good old BFS tree algorithm. Okay, so you started with a node. So let's say you started with node A. In this case, they started with node A, and they have formed this BFS tree. So A's neighbors are B and C. So B and C are here. Uh, but then B's neighbors are D, E, and C. But you only have D and E in layer 2 because C was already discovered before. So here is a dashed edge. So that dashed edge is showing the fact that this edge is not part of the tree, but it was part of the original graph. So that's what they're saying. The edges in the graph minus T are shown as dashed segments. And note that every layer of T has at most k vertices. So in this case, what was the value of k? It was 5. And in every layer, there are 4 vertices. Okay, so this is the good old PFS running on the graph. And they have chosen this vertex. That is crucial. But from this BFS tree, how would one find a valid tree decomposition of width? So how would one find a valid tree decomposition? I'll write TD for small of G of width at most 2k minus 1. So that is a challenge. Uh, Important observation is that it was possible to ensure that in every layer of the BFS tree, there are at most k vertices. Now, can this information be exploited to sort of get valid tree decomposition of G of width at most 2k minus 1?
So how does this ensure that the maximum number of the vertices at a particular level would be less than k vertices? Because if we conducted DFS, then we have no control. It depends on the structure of the graph as well.
Yes, 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 yes. So how this was, so if you had started, let us say if you considered C to be the root of the BFS tree, then you will end up having A, B, E, G, and H, 5 vertices in layer 2. But they don't want to avoid 5. So of course, there's no question of taking a vertex whose degree is already 5. So they started with A. So your question is, how was A chosen to be the root of the BFS tree?
Yes, because once we start searching the graph, initially we can have control, but then later on we lose the control because this will depend on the structure of the graph. That how many vertices are there at a particular level. We will only conduct the search level by level without having any control over the number of vertices in a particular.
Yes, yes, yes. So I think so that answer to that question would be in the videos. But let's give it a thought. Is it trivial to sort of make the right choice of the BFS tree?
I think that in BFS there is a concept of branching factor kind of thing. So, but how will that help?
So this is the max. Let's look at the book. I'll look at the book. So this is the max leaf spanning tree problem. So the running time, as I can see, the running time has exponential dependence on k. So the running time of this algorithm turns out to be 4 to the power k n to the power constant. So you know k, and somehow in 2 to the power k or 4 to the power k time, you want to be able to identify the correct leap, correct route. From here, you will start the BFS.
Yes, I could not understand this.
You have n choices for the route. Let us say the number of vertices is n. So you could have started the BFS at any of these n vertices. Now, so the thing is, even if you do it, if you enumerate it, if you even if you do it n times, you will get n different trees. And if all these n different trees are such that uh, there is at least one big layer. So if you cannot avoid having a layer of at least k vertices in any of these
Yeah,
n
so,
different BFS trees, then you don't have any hopes.
yeah, so I have a small observation here that why don't we focus on the degree? So say if we have the degree of a vertex greater than this thing, this amount k, then we will ensure that that vertex is once we reach to C. So then, yeah. So at every point, I mean at every layer, before expanding it further, we will compute the sum of the degrees of the vertices. Like here at the layer one, we will compute the sum of the degrees of B and C. So the degree of B and the degree of C came out to be 1, 2, 3, 4, and 1, 2, 3, 4. So the sum came out to be say 8. But repetition is has been eliminated here. Is this so? Because from B we are moving to, oh, I see. Degree won't help because we are, so I shall only be moving forward. Degree won't help.
So it is not clear that in so even if you started with uh, even if you started the BFS at a vertex whose degree is small, it may end up going and traversing a path, and in some situation you have more than expected, more than desired number of vertices in some layer. So I don't know whether there's a clever way to choose the vertex at which the BFS should be initiated. But even if you the brute force, I mean, even if you apply brute force and if you be naive, you will at most make n different BFS trees. So your running time will at most go up by an order n factor, which is consumed within this into the constant. And then you can choose that BFS tree which suits your needs, that is, in which every layer has at most k vertices. If it does not exist, then you have no hopes.
Yes, yes, it seems okay to me because VFS requires almost a linear time. I think of the order of v plus t. So
Yes.
uh, so it's okay that if I explore all the if I start with all the vertices and finally uh, get the desired form. Seems justified.
Yes, yes. So even that doesn't hurt much because we have the liberty to have a running time of this sort and to the constant. So let's believe that there's, uh, I mean, I don't know what they have done in the video, but even if you do it naively, there is not much we are going to lose. Uh, but so far so good. After you form the BFS tree, which uh, respects your desired property, that none of the layers is too large. So in every layer, there are at most, in this case, five vertices. This is the largest layer having four vertices. Now, can I use this BFS tree to ensure that I have a tree decomposition where tree width is at most 2k minus 1. So that means that back size is at most 2k. That is the question. So let's look at the question, that what is the end of the question. So as discussed in module 5, lecture 24, find the tree decomposition of G of width at most 2k minus 1. So in all these cases, uh, the back size, uh, what is the largest back size? In option B, the largest back size is 6. So 6 minus 1. So width is 5. So all these cases looks like they're valid, but there is only one correct answer. So there should be some way to get to the correct answer from this tree decomposition. So we'll see that. So observe that if you look at two consecutive layers in the BFS tree, so let us look at layer 1 and let's look at layer 0 and layer 1. Okay. Uh, then there could be edges between the vertices of layer 1 and layer 0, and there could be edges among the vertices of a given layer also. But can there exist an edge in the graph between layer 0 and layer 2?
Can you repeat your question?
Yes, yes, yes. Can there exist an edge in the graph G between layer 0 and layer 2 vertices?
Yes, yes, there 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 will be there will be.
So if there is a edge, if there's an edge between A and H, let us say, a vertex in layer 0 and a vertex in layer 2, then this vertex H would be a child of vertex A, and it would be discovered while doing BFS in layer 1 only, isn't it? So BFS follows like that. So it starts at A. If you have started the BFS at A, then all its neighbors will be explored in layer 1. So if
Yes,
H itself was directly connected, then H would have been a neighbor, and it would have been explored as part of layer 1 formation only.
Yes, yes.
So this is not possible. So no, that is not possible. So this gives a useful information to us that if I merge all the vertices in layer 0 and layer 1, then I will not have to. So what I mean to say is, if I merge the vertices of layer 0 and layer 1, or for that matter any two consecutive layers, then I don't have, since I don't have edges which are from layers below, so therefore all the neighbors of A are explored. So to see it even better, if I merge layer 1 and layer 2 together, then all the vertices of layer 1 have their edges uh, till layer 2 only. Means after layer 2 there are no edges. Okay, so using this fact, there's easy way to draw the tree decomposition. So the rule is the following. So you make the bags like this. You make the bags like this. So this bag is the vertices in layer 0 and layer 1. This bag is vertices in layer 1 union layer 2. This bag is layer 2 union layer 3, and so on. So we have 4 layers. We have 3 layers only. So lastly there should be a bag which is the last layer. Okay, and then you connect the bags in a path. So what happens? Let's do it for this graph, for this tree decomposition. Layer 1 and layer 0 are merged, A, B, C. So this is my first bag. Layer 2 and layer 3 are merged. So this is my second bag. B, comma, C, comma, D, comma, E, comma, G, comma, H. And then I have layer 2 and layer 3 merged. So I have D, comma, E, comma, G, comma, H, comma, F. And then lastly, I have layer 3. Now, why is this a valid tree decomposition? So we have to verify the 3 properties. One is every vertex is in some bag. So by virtue of the fact that every vertex appears in at least one of the layers, so there must be a bag containing every vertex. Okay.
Yes.
Now, for every edge, I want to see a bag. So every edge is in some bag. So now, what are the edges? The edges are between consecutive layers or among the same layer. There are no edges which are not, so there are no edges which have a jump from one layer to uh, a non-consecutive layer. So the edges are all within layers or within consecutive layers. So therefore, for every edge, we have a bag. All right.
Yes.
Okay. Now the crucial property is the connectedness property. So connectedness properties. So you consider any vertex. Let us say this vertex G. So those bags where this vertex has appeared, they should be connected. Okay. So now, uh, which all layers? So first of all, G is part of one layer, so layer 2 only. So, uh, so which bags have layer 2? This is the one bag, this is the other bag. But layer 2 bags are adjacent to each other, so they must have a connecting edge. So therefore, all the bags that contain G, they form a connected component because of simple adjacency, because we have connected the uh, bags in a path, and in the path, the layers are sort of consecutive. So layer 2 is appearing only in adjacent vertices, bags. So therefore, connectedness with respect to every vertex is also satisfied. And why is the width at most 2k minus 1? So why is the back size at most 2k?
Uh,
Because
yeah, the way we have merged the layers. So in every layer we have at the most k number of the vertices. So therefore this will be
yes,
less.
so two layers have been merged at a time. So two layers together at most have 2k vertices. Now therefore the back size is one less. I mean the width is one less. So that is how you have found a valid tree decomposition. So this is the final solution. So one is ABC. This is connected to BCD EGH and DEGHF and F. Let's see what is the answer. ABC connected to BCD EGH, connected to DEGHF, connected to F. So this is matching with what we have computed. So this is although part of solving another problem, which is the max leaf spanning tree problem. But in the process of solving the problem, you make use of this tree decomposition, which helps you design a solution for this problem that runs in so much time. So now we'll see that how the algorithms, after you have done the tree decomposition, how you can exploit the tree decomposition to design a fixed parameter tractable algorithm that we will see in the next question. So what is the time now? It's 6:53. I think another question can be done before 7. Then we can take a break. This is also about tree decomposition. This is also very easy. So let you read the question. So K path, uh, we discussed K path, but again, K path is given a graph and number K. The question is, can you find a simple path, that means where vertices are not repeated, of length K or at least K? So again, this is a NP hard question. So you want to find a tree decomposition, but this time you are going to find the tree decomposition via finding a DFS tree instead of a BFS tree. Last time we had used the machinery of BFS tree. Now we are forming a DFS tree and it is rooted at a given vertex R. So R is not given. You run the DFS at R and you obtain this DFS tree. Now, how shall you exploit the properties of the DFS tree to compute a valid tree decomposition of the graph?
Yes, and can you repeat the definition of the k-path problem again? What we need to find?
We need to find a simple path within the
Mhm.
graph of length k. That means there are k vertices in the path. Length k means k vertices in the path, not k edges. So as per the convention of the videos, uh, k path is a path which have which has k vertices, k minus 1 edges.
Mhm. So here also they have used the dashed segments, and this says that like here we have an edge from R to B, and so this is via R to A and then A to B, but we have excluded R to B because this is the direct one. And yes, so
Yes. So the difference in BFS and DFS tree is that in BFS tree, we could say that between a layer 1 vertex and a layer 3 vertex, there cannot exist an edge because of the argument we have seen. But here, what can happen that uh, you go down the tree and at some layer there is a vertex which is connected to the root, which is possible. For example, in this case, B is connected to the root R. So how should the bags be defined? So the bag should be defined with respect to the leaves. So in this case, there are three leaves, B, C, and E. So you consider the path from the root to the leaf. So I'll just show you the answer. Okay. So consider the path from root to B first. B is the leaf. So all the vertices in this path you take and make it one bag. So R, A, and B are in one bag. And next, again, consider another leaf, C. So consider the path in DFS tree from root to C. So again, R, A, and C are in this path. So that is the next bag. The next bag is again with respect to the leaf E. So R to E path has R, D, and E. Therefore, that is the next. Now we have to appreciate that this is a valid tree decomposition. So first is uh, whether there is a bag for every vertex.
Yes, yes, there is. There is.
Yes, so every vertex must appear in some root to leaf path. Therefore, there must be a bag for every vertex. Now, every edge should also appear in some root to leaf path. So therefore, for every edge also there is a bag. Now, for every vertex, the connectedness property should be ensured. That means, uh, so all the bags that have a given vertex should be connected. How do we see that?
So like here, RA and AB, and then so if one vertex is there in the multiple bags, so like here R and A are there in the multiple bags.
Mhm.
Um, so it shows that I mean an element would be there in the multiple bags if somehow they share the parent and the child relationship kind of the thing. So therefore, an age is mandatory to occur.
Mhm. Mhm. Okay. Yeah.
So
So can we say something by contradiction? Can we assume that, okay, that is not the case? There is a vertex. So let's try to argue it formally. So suppose you have done this decomposition as per the rules that we have defined, and you have this set of bags, and these bags are sort of connected in a path, and so on. So now there is a vertex, let us say V, which is in two non-consecutive bags. So V is not here. So V is not here. V does not exist here. Okay. Uh, so then we have a violation. But if this happens, so observe that these bags are corresponding to some root to leaf path. So let us say this is corresponding to leaf 1, this is corresponding to leaf 2, and this is corresponding to leaf 3. Okay, so now you know that if you are moving from the root to leaf 1, you encounter V. If you are moving to root to L3, you also encounter V. But when you move from root to L2, you don't encounter V. Then how does it look? So how can it look? Let's see. Let's see. So there is a root, there is a path, and this path leads you to L1, and you consider this entire path as part of bag 1. And then there is another path. This path brings you to uh, L2, and there is another path. This path brings you to L3. So there is a V here. So because V is sort of common between these two paths, R1 to L1 and R1 to L3. Therefore, in both the bags to L1 and L3, V exists. But uh, in the path from R to L2, V does not exist. That is fine, isn't it?
Yes, yes, it's okay. It's okay. So therefore, there should be connectivity in between L1 and L3. Uh, Interesting. So, so but then, I mean, where is the violation here?
Yeah. So I am trying to see what what is a violation. So we do not say a violation, right? So there is a bag which contains V. There is another bag which contains V, but there is a bag in between that doesn't contain V. So uh, so the thing is, uh, you have to process the leaves from left to right in the sense that L2 cannot be here. Uh, so when you do the DFS, uh, you keep reporting the vertices. So first you report the root, then you go deeper, 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 deeper like that. Then you take care of all these vertices. Then you come here and so if L3 is discovered before L2 in the DFS traversal, then you wouldn't have drawn the back for L2 before the draw back for L3 because L3 is discovered before. So you have to draw these bags in the order of discovery of these leaves. So therefore, such a path cannot exist at all because L2, by virtue of being uh, uh, between L1 and L2's bag, L2 must have been discovered between L1 and L2. So L2 should have been discovered somewhere here. And because L2 were here, therefore, in the path from root to L2, V would have appeared. So there should have been a V here. Does it make sense?
Yes, yes, to some extent, yes.
So the thing is, the bags that we have drawn,
Mm-hmm.
we must draw it in the order of discovery of the leaves. So we have drawn a bag for every leaf. Let's look at the picture again. So here is the question. So now you're doing an DFS from R. So how will it look? R, comma, first you explore R, then in the traversal, what do you report? A. After A, what do you report? You might report B or C. Let's say you report B, but after that you report C. After that you go back to R and then you report D and then you report E. So in terms of the DFS traversal, B is the first leaf, C is the second leaf, and E is the third leaf, which have been reported in this order: B followed by C followed by E. So
Mm-hmm.
therefore, the bag that corresponds to the root to leaf path, root to B path, should be followed by the bag that corresponds to root to C path, should be followed by the bag that corresponds to root to E path. So that's what they have done in the figure. RAB, then there's a bag RAC, then there's a bag RDE. So if you retain this order of the discovery of the leaves in your order of the bags, then such a situation will not arise that there are two bags like this where there is a common vertex, but there is another bag in between that doesn't have that vertex. That cannot happen because of retention of the discovery of the leaves in the bag formation.
Yes.
So give it a thought for some time. That with this rule, what we have seen, it is a valid tree decomposition, and then we'll move to the other questions. So we can take a break here at 7:06. What time shall we resume?
Yes, so but today is a really festival day, so it's possible that we stop it early today.
Oh, okay, fine. So do you want to continue and finish by 7:30 or so?
Yes, yes, that would be
Let us
better.
see if there is anybody else. Just a second, so that I'm not looking at just a second. There is one more person, Raghunoor. Raghunoor, is it fine if we finish earlier? What festival is today?
Yeah, so
Oh,
today,
Krishna Janmashtami. Okay, okay. There's Janmashtami, right? Uh-huh. Okay. We'll finish by 7:30. Yes, I just forgot.
yes, thank you so much. So we'll meet at a break or we'll continue.
You want to break? Then we can break. Otherwise, we can just look at two more questions and finish.
Okay, sure, sure. Then we can continue.
Or let's take a break. I mean, maybe 7:15 we'll take a short break. 8 minutes. 7:15 we'll resume and we'll finish in 7:30 by 7:30.
Sure, sure.
All
Thanks.
right, fine. Hello, shall we start again?
Yes, yes.
Okay, so this is one of my favorite questions. It's very easy to explain. So I think this will be the last question. We should be able to finish in next 15 minutes. So there is a graph. There is a tree. In the graph, this problem is NP heart. So in this tree, uh, we want to find the independent set of maximum weight. So every vertex is assigned a weight. We want to find the maximum weight independent set. So on trees, it is polynomial time solvable using DP. So they have formed a DP table. And the question is, what are the values of these two missing entries, AR and BR? So first, let me copy these two pieces of information, then we will compute these two values. Is 4 or 5? What is the question number? Just a second. Okay. It's question number 4. Okay. So you have a graph. In the graph, it is not possible to solve it in polynomial time. You have a tree. So I will write down the weights on the vertices. So R has weight 4, A has weight 3, B has weight 3, C has weight 3, D has weight 3, P has weight 2, Q and S are all 2. You want to find the maximum weight independent set. We can do that by looking at the figure. But there's a systematic DP to do it. So this is use of DP. So what it does is it defines two quantities, A and B, with respect to each vertex. So A of a given vertex is the maximum weight independent set in in the subtree rooted at V. So TV is the subtree rooted at vertex V. So if you say that, okay, I am looking at a particular vertex, let us say vertex P, then if you look at the subtree rooted at P, which is P itself, what is the maximum weight independent set at P? So because it is single vertex, that is why it is 2. So let's look at a internal node. So this is B. So what is the maximum weight independent set for the subtree rooted at B? So within this, so we can see that if we take B, then we get weight 3. Otherwise, we can take P and Q. We get weight 4. So 4 is better. So that's why it's 4. So that is the definition of A. Now, what is the definition of B? It is the maximum weight independent set. Again, in the subtree rooted at V, but not containing V. So if you do not take the vertex V in the maximum independent set, then what is the maximum weight independent set in this subtree? So is the definition of A and B clear?
Yes, yes. And so can you illustrate the meaning of the B of V and corresponding to the small v value is 4 in the first row. So this
Okay.
value 4, why so becomes?
So consider the vertex B and the subtree rooted at B. So
Mhm.
now you're not allowed to take B, that is as per definition that don't take the vertex at which you are computing the value. Now, so you because you're not allowed to take B, you will take its two children because they are independent. There is no edge between P and Q. It's a tree, and P has weight 2 and Q has weight 2. The sum of the weights 2 plus 2 is 4. That is why this entry corresponding to B is 4.
Mhm. And the lower entry is also 4. Why so? Because it gives the maximum weight independent
Yes,
set
yes,
in.
yes. Yes, in this piece. So if you had taken B alone, then you cannot take P and Q, because as soon as you take P and B are connected. So if you are saying that I'm going to take B, then P and Q cannot be taken because we want an independent set. So you can at most take P alone, which will give you weight of 3. And if you
Mhm.
don't take, then you will get 4, which is better, much better than 3. You want to maximize weight, as much weight as possible you want to take in the independent set. So that is how
Yes.
they have computed all these entries. Now the question is, how shall we compute A of R and B of R? That's all. There's nothing beyond that. That's all we want to do. So it's easier to compute B of R. So let us first compute B of R. So what is B of R? B of R is, you are allowed uh, uh, to take. So what is B of R? You are allowed to take uh, all vertices but the root. So subtree rooted at R is the entire tree, but you are not allowed to take R because we are computing B of R. So if you're not allowed to take R, then you can take the maximum independent set in this child of R plus this child of R plus this child of R plus this child of R. So because these subtrees rooted at the children are also disjoint, so the question of overlap will not arise. So you can just take the sum of the weights of the maximum weight independent set at these 4 children. So B of R would become A of first child of R is A, plus second child of R is B, third child of R is C, fourth child of R is D, isn't it?
Yes. Yes.
Yes, these things we have already computed. So
Mm.
A is this 3. So that means that if you take the maximum weight independent set rooted at A, including A, you will derive a weight of 3. Similarly, from the subtree rooted at B, you will get a weight of 4. Similarly, from the subtree rooted at C, you will get a weight of 3. And from D's subtree, you will get another 3. So these things, 3, 3, the 9, 9, and 4, 13. So therefore, BR, this entry is 13. Okay. Now what is AR?
Yes. So for the AR, then I'll take I'll take the sum of all the B values and I add the value of R into it. So what is AR here? So AR is the maximum weight independent set and rooted at the this
R.
R. Yes. So for that, this R should not be included then. So if R is not included, then I need to take the sum of all the B values.
No, so in R can be included. There is liberty to include R in the independent set.
Yes.
That is the definition. This is the
Mhm.
definition.
Mhm. Okay.
So, but if you take R, then you do not take any of its children. If you take
Mhm.
R, then you cannot take ABCD, but later the grandchildren level you can take.
Yes.
Okay. So there are two possibilities. Either you take R or you don't take R. Okay. So if you take R, then
Mhm.
you will get a weight of R.
Mhm.
Plus, additionally, at the children of R, you will take these guys. That means you're not taking the children, but you are taking the maximum independent set at the children while not including the children. So weight of R plus B of A plus B of, that means the sum are the children. This you can calculate. You already have calculated. So that you have taken R, but none of its children, and you're taking the b values at the children. That means those independent sets which do not include the children, but not including the children, what is the maximum weight that can be derived? So that is one possibility. The other possibility is that you do not take r at all. And if you do not take r, then you take the sum of the a values. So basically, you take br. Then br is the best you can do while not including r. So br you have already calculated. This is 13. Now we do not know what this is. This is weight of r is 4. So this I will do the calculation here. So weight of r is 4 plus what is b of a? B of a is 0. B of b is 4. B of c is 0. B of d is 2. So 2 plus 4, 6. So you might get 6 plus 4, 10. So you have taken r, but since you have taken r, you have not taken anything from its children layer, but from outs again from the grandchildren you can take 2 plus 2 plus 2. So you will get 10. That is what it is showing. Visually also we can see, but better to take br. That means don't take r, take the children of r, which together give you uh, sorry, yeah, take this guy, these two, these and this. They together give you 13. So AR is also 13. Are there any questions on this?
No.
So this is the simple DP algorithm for finding the maximum weight independent set in trees. This problem is notoriously hard for graphs. It is one of the hardest problems when it comes to solving optimization problems in general graphs. And even in special cases, it is most of the time very hard. But for the special case of trees, it is polynomial time solvable using this dynamic programming approach. It is a
Yes.
very popular question given in the exam, and whenever algorithms courses are offered, it's a it's an example of how DP uh, can work wonders. Okay, so fine, so far so good. I think we have 2-3 minutes. I'll just let you. So the other questions that we had, so this question was also on independent set, but this is again a special case. So this is called a grid graph. So instead of a tree, you have something called a grid graph. So in the grid graph also the DP will work. So what is a grid graph? So you have a grid, and you can only connect edges between two adjacent vertices in the grid, and then you can sort of so they're saying C1, C2, C3. So column 1, column 2, column 3. So column wise, you can process and run a DP. And similar thing is possible for maximum weight independent set. And then there's some separator based questions. So how do you find a vertex that sort of deletion of which separates the graph into two components of roughly equal size? That again is it's not very difficult. Again, there's a grid based question where tree decomposition can help. And the last question again, so you have a tree, and from this tree you want to get what is called one width tree. That means you want to achieve uh, tree decomposition where every back size is at most 2. This is very simple, like just the same thing you have to copy, and the parent to child you have to club. So the root doesn't have any children, so it is as it is. A has So the root doesn't have any parent, so it is as it is. A has a parent R, so A is clubbed with its parent. T's parent is A, T is clubbed with its parent. So for every vertex in the tree, you club it with its parent. The root does not get clubbed to anything because it doesn't have a parent. So that is how you'll get a one width tree decomposition. So that's all we wanted to discuss. I think, yeah, so we'll finish now. And I forgot that today is Janmashtami. So happy Janmashtami to
Same to
both of
yeah.
you.
I have a question here. That is there any good resource on dynamic programming? Because once a solution is given, then I mean I can understand the solution pretty easily. But then to solve a fresh problem,
Yes, yes. So Jeff Erickson's book is very nice. I like the exposition of Jeff Erickson's book. They're very nice, very story-like exposition. So I would suggest that you can read the chapter of dynamic programming from the book of Jeff Erickson.
thank you so much. Yeah,
Okay,
nice.
thanks a lot. Good night. Yeah, take care.